Hi everyone, welcome to our video on using one equation to create another equation that would be differentiable so that we can optimize. In our scenario here, whenever you see optimize, you're thinking maximize or minimize, and so it's usually find the equation and then afterwards take the derivative and set it equal to 0. All right, so in this example, it says Amy owns a ranch with 11 apple trees. Currently, each tree produces 50 apples each season. She wants more trees, but assumes for each new tree planted, each tree will produce 2 less apples due to sharing water. How many trees should she plant to maximize apples per season? Okay, so we want to maximize. Let's use the color here. So maximize. So we want to maximize apples. And so this doesn't have like an exact equation immediately. So it's not like the area of a triangle or something like that. But we do want to maximize apples. So I'm just writing it down real quick. Okay, and then now let's break down what we have so far. So we'll come back to this. We'll need an equation. Okay, so it says Amy owns a ranch with 11 apple trees. Currently, each tree produces 50 apples each season. Okay, so let's get this. I'm going to underline this in the blue the best I can there, squiggly line. Okay, so if she has 11 apple trees and each tree produces 50 apples, then the way I'm going to write this, let's create a total apples equation. Okay, so we'll say total apples, which I'm just going to say is capital T for total, is the number of trees. Okay, so let's write it as number. Let's put it above. No, let me spell. Can I spell? Okay, so the number of trees times the number of apples per tree. So number app per tree. Okay, so currently, I wrote that above in words so I could put the numbers in. So 11 trees, so number of trees is 11. Times the number of apples per tree is 50. So currently her total is 11 times 50. But we want to use this to create another equation. So it says she wants more trees, but assumes for each new tree planted, so each new tree planted, each tree will produce 2 less apples. Okay, so each tree produces 2 less apples. Okay, so let's do it like this then, where we have for each new tree planted, so we're going to say that's going to be an addition of x. Okay, so plus x is our new tree planted. So let's adjust this. Okay, so our new total, we'll do t equals 11, and then we're going to say plus x for another tree getting planted. And then we just have to look, well, for each x that we add to 11, we would have to minus 2 from the apples, so 2 less apples. So let's do minus then, so 50 minus, it says, so 2 less apples would be minus 2x. Okay, so for each tree, so each tree added, so plus x, so if we have one tree added, it would be 12 trees, and then we would have 48 apples. Adding another tree would have 13 trees, minus 4 apples would be 46. Okay, so we can kind of check it in our head as we go. Okay, so the 2 less apples was, well, let me go ahead and mark it in the red, was minus 2x. And we're just making sure we attached it to the correct set of parentheses. So the trees in the first one, the number of apples in the second one. Okay, so that looks like our equation then. This is our total equation. Okay, so we want to maximize apples, our total apples equation. So let's take this. So this was all just our scratch work. And then, so we want to maximize apples, which we're saying is t equals that 11 plus x times 50 minus 2x. And then now we could start to FOIL this. Okay, so let's go ahead and say that the t is equal to, so 11 times 50 would be 550. And then minus 22x, and then plus 50x, and then minus 2x squared. Okay, so I just FOILed that out, and then let's go ahead and rearrange it. Let's put it in descending order, and at the same time, let's collect like terms. So I have negative 2x squared, and then this looks like it's plus 28x, and then plus 550. Okay, so this is the total tree, or total apples now. T is for the total apples for this adjustment. Okay, and so if we want to maximize this equation, we would need to take its derivative. So t prime is equal to negative 4x plus 28. And then now that we have the derivative, we set this equal to 0. So we have 0 is equal to negative 4x plus 28. And then, well, I could add the 4x over, so we get 4x is 28. And then it looks like I can solve this and get x is 7. Okay, so that plus x was the addition of each tree. So it looks like she should add 7 more trees to get the maximum amount of apples. So it says how many trees should she plant to maximize apples per tree. So she should plant, we can put this in words, she should plant 7 trees. Okay, and just to kind of check it, okay, so let's do, so here's our original. T equals 11 times 50, which is 550. So that's the number of apples with no adjustments. And then adding 7 trees would be 18 new trees. So new. Our T would be 18 then, because 11 plus 7 new trees is 18. And then we'd have to minus 2 apples per tree. So we would have to minus 14 apples from 50. So that would be 36. And well, 18 times 36, I don't know that immediately. I'm going to use my calculator again and just plug it in to see it. So 18 times 36 is 648. Okay, so that's bigger than 550. Okay, so that looks like it's the best one. And you could try other scenarios. This 648 would be the biggest number. Okay, so it looks good. 648 is the maximum number of apples. So if it asks what is the max apples, it would be 648. Okay, so that's how we could break these down. So notice again, it's kind of similar to our other ones where I set up maximize or minimize what's important, use some other information in some way to get this more important one going. Okay, so let's try one other where it says a taco truck sells 160 tacos per day at a price of $2 each. A mathematician shows that for every 25 cents reduction in price, 20 more tacos will be sold. How much should the deli charge for each taco to maximize revenue? What is the maximum revenue? Okay, so the taco truck, I guess, is called the deli here. Maybe that's probably a typo. We'll just say truck. How much should the truck? There we go. Okay, so we'll try to fix that in the notes. Okay, so a taco truck sells 160 tacos per day at $2 each. That's important to us, but let's also break this down. They said maximize revenue. Okay, so we want to maximize revenue. And we know revenue is equal to price times quantity. Okay, so currently, let's break this down. It looks like, let me not write over it. It looks like they say they sell 160 tacos, so that's the quantity. That's the current quantity. So let's put that over here. So our revenue equals, so the price was first. So we have, here's our price, here's our quantity. So we have 160 is our quantity at a price of $2 each, so 2. And so we could multiply that and see it's 320. Okay, anyway, but we want to adjust this. So it says the mathematician shows that for every 25-cent reduction in price, 20 more tacos will be sold. Okay, so now we have to adjust this. So it shows for every 25-cent reduction in price. Okay, so for every 25-cent reduction, so that means that's a minus 0.25x is how we'll attach it to the price. So let's go ahead and start writing it. So we have R is 2 minus 0.25x So X is, so we're just attaching the variable to the reduction price. 20 more tacos will be sold. Okay, so the 20 more tacos, that means plus 20x, which gets added to the quantity. So we'll do 160 plus 20x. Okay, and then that's about it. So notice how similar these types of problems are. And then this is our revenue function. And so now I can start to work with it. So back to the black ink, I've got my revenue is this expression 2 minus 0.25x times 160 plus 20x. And then we'll FOIL it to make it easier. So we'll have 320 and then plus 40x. And then this is the negative 25x times 160 would be minus 140x. And then this multiplies this one, and we would have minus 5x. Okay, so we have x squared, actually, minus 5x squared. Okay, and so in this scenario, we would continue simplifying. All right, so we have our revenue is equal to, let's go ahead and put it in descending order, minus 5x squared. These combine to make 0. So here we've got something interesting happening. Okay, so that combines and makes 0. And then we're left with plus 320 at our end. Okay, so this is our revenue function, and then now we have our derivative that we would want to find. R prime would be negative 10x. So that's it. So it's just negative 10x. And then, well, we would then say, hey, shouldn't this be set equal to 0? And then we would try to solve. But this is a strange equation because when we solve, we get x is 0 is the only answer. Okay, so this can happen sometimes. So x equals 0. This is saying don't do any adjustment. So the mathematician was wrong. Okay, or even I guess the mathematician could show that that could happen, but it doesn't help with the way that this works. Okay, so here we've got an interesting scenario where the number of tacos should not change. Okay, so how much should the truck charge for each taco to maximize revenue? Well, I don't want to change this at all, so I don't want to subtract any 25 cents from it. Okay, so this means let's not do any of them. Okay, so they should still charge. So we should say the truck should charge $2 still. Okay, because there was no increase. X was 0, so I shouldn't subtract anything. We should just charge $2. And then what is the maximum revenue? Well, if it stays $2, then our revenue, oops, let's just write it as R, would equal this price, the $2, times the original quantity, 160, which is $320. So the truck should charge $2, and then the max revenue is $320. Okay, so this one, the number of price changes shouldn't have been any. All right, so that's a unique case. I wanted to do that just to get one, but most of the time it's like the first one with the plant, with the trees. Okay, but notice it's pretty much the same thing, pretty much the same scenario. We just have to make sure we know how to interpret that final answer. Okay, so that's it. If you have any questions, please let me know. Otherwise, thanks for watching, and I'll see you next time.